This time around, we're discussing viscosity, surface tension, and capillarity. Looking at the fact that these are quite important as well in the behavior of fluids or in the analysis of how fluids behave. So take them one by one so that we can see how they can be analyzed as applied to fluid mechanics. So there's some terminology that is quite critical that we may need to understand from time to time. The first one is cohesion. Now, cohesion refers to the tendency of a liquid to remain as one assemblage of particles. You see this very common in where liquids may form like what look like bubbles on surfaces. So that sticking together, coming together into those little particles, that is cohesion. Now, there is adhesion. To adhere is like to cling. So what happens is that the molecules of a liquid will normally align themselves with the boundaries or solid boundaries of where they are being contained. So what you see there is adhesion. And this one is very common. You can even see the color of the liquid that was used in a particular container because of adhesion. They adhere to it. Then we also have what is known as capillary action. In capillary action, you bring together the two properties we've talked about, which will cause a liquid to rise to some level. Then that is what we can consider to be the capillary action. And as you can see, you can insert a capillary tube. Those that are sticking together will rise to some height, clinging to the walls, making some angle theta. And that will be how they will behave. So the height to which they will rise is h. Some point we'll talk about that. This is the free surface of water, which others can say the level of water or the level of the liquid that you're dealing with. So first of all, we have what is known as the surface tension force per unit length. This is force per unit length, meaning it should be newtons per meter. If you want to get just the force, you need to multiply by how many meters you have, then the meters will cancel and you remain with your force. H, that's the height. Theta, that's the angle of contact, as we saw in there. D, that's the diameter of that capillary tube that was being used. Then, of course, we already know that when we want to know the weight is pressure times area, that will give us the weight. But since we already know that pressure is given by omega h and area is by d squared over 4, then we can write it as the weight of the liquid is equal to omega h representing the pressure and the area represented by pi d squared over 4. Now, what next? If we consider the vertical component of the force, there where we have the tube, it is this surface tension or the force per unit length, surface tension force per unit length, multiplied by the total length given by the circumference of the tube, which is pi d, multiplied by the angle. So this force is the one we're talking about. All we do is now equate it to the other force we had there. And already you can see the pi's being common, pi d, pi d. So once you proceed, you find that your height is going to be 4 by this surface tension force per unit length multiplied by the angle, and then specific weight times the diameter of the capillary tube. This is the height to which the capillary will rise, or we call it the capillary rise height, or the height of capillary rise. Then surface tension, we simply said this is caused mainly by cohesion on the free surface. That's what happens there. And when we refer to it, we have already said the pressure force is P times pi d squared over 4. But there's one more case that we're yet to talk about. In case this is pi d, like we mentioned earlier, then if you have to make it the subject of the formula, it will be that pressure is 4 surface tension over d, just pressure alone. You're looking for pressure. Because on this other side, this is the force, and this is also the force. Then, meaning that going ahead, if you go ahead and now talk about a soap bubble, you say 2 pi d instead of pi d. So there, it means that the difference will be, instead of having 4 here, you end up with 8. So the pressure will be 8 rho over d. This is 8 times the surface tension force divided by the diameter of the capillary tube. What is compressibility? Of course, here, that just refers to the property which allows a fluid to undergo some change in volume. And of course, we also have the bulk modulus. The bulk modulus, what it will do is compare the compressive stress and the volumetric strain. You can liken it to Young's modulus, which is the ratio between stress and strain. So here, we're saying the volumetric strain, that is the ratio between the change in volume and the original volume. So that's what we have there. Hence, K itself can be increased in pressure over volumetric strain. And hence, we have dP over negative dV over V, referring to the summary of this formula, because we're saying volumetric strain is changing volume over the original volume. So that increase in volume is on top. Then below there, you can have that volumetric strain coming out. Now, here, you can still have dP over that one, because here what you are simply doing is to make that bulk modulus the subject. So you can have dP, or the change in pressure, divided by the volumetric strain. So increasing pressure or volumetric strain. This is our volumetric strain, and that is in our pressure. Now, here, this is just an illustration to talk about how from the original volume, we have the change in volume when a material is undergoing compression, and then compressibility being 1 over K. Let's go back to viscosity. Viscosity, we had said that this is the resistance to the flow of fluid. And accordingly, the shear stress is proportional to the change in velocity with respect to the thickness of the fluid, or the distance or the distance between the plates that are sliding over each other, as we shall soon see. If you look at this, you can introduce the equal sign, which gives us now this item we've been looking for. This constant is the coefficient of dynamic viscosity. The constant is our coefficient of dynamic viscosity. So that is what happens, and this is how you do that. Meaning that if you have to make shear stress, this dynamic viscosity, the subject of the formula, you may have to, just a minute, you may have to just maneuver around with this formula and make dynamic viscosity our subject. This is the viscosity of our liquid. Now, there is also what is known as kinematic viscosity. This is the ratio between that dynamic viscosity and the density of fluid given by that symbol. Then we also have what is known as Newton's law of viscosity, where the shear stress on an elemental layer of fluid is proportional to the rate of shear strain. basically referring back to our definition of viscosity, where we're bringing together all this. So we are basically reviewing that formula. And now we can also talk about the types of fluids. There's what is known as an ideal fluid. An ideal fluid is incompressible and has no viscosity. In other words, we don't have such a fluid. If a fluid has no viscosity, then does it even qualify? Because however negligible, it should have some amount of resistance to flow. Then that is a fluid. Then the other one is a real fluid, the opposite of that. So there, the main item is that this fluid has viscosity. That is a real fluid. Away from that, we have what is known as a Newtonian fluid. So this one, it's the proportionality that we're interested in, where we're saying that the shear stress has to be proportional to the rate of shear strain for such a fluid. And it has to be a real fluid whose proportionality is agreeing. It's working like this, where we are saying the shear stress is being proportional to the rate of shear strain. Then that is our Newtonian fluid. Non-Newtonian fluid is a real fluid which does not have that proportionality we've referred to. Then we also have an ideal plastic fluid. So here, we have a case where the shear stress is more than the yield value. But that shear stress is also proportional to the rate of shear strain. Then we are saying this one, yeah, this one's supposed to be strain. A small correction, that should be strain. That is our ideal plastic fluid. Let's apply this. Here is an example where the plate at a distance 0.05 millimeters from a fixed plate, the speed of movement 1.2 meters per second. It requires a force of 2.2 Newton per square meter, per unit area to maintain that speed. Then we're told to determine what the viscosity of the fluid is. That fluid sitting between the two, what is the viscosity? What have we been given? We've been given the speed of movement of the plate. We've been given the thickness, the distance between the two plates, 0.05 millimeters. We are not going to leave it in millimeters. We convert it to meters because it's in meters per second. So as per tradition, we divide this by 1,000. When you divide this number by 1,000, what you get is 5 times 10 raised to the power negative 5. Then the force is 2.2 newtons for every 1 square meter. However, this is the definition of stress, in this case, shear stress, because the plate is sliding on top of that lubricant. So then, force per unit area is basically our shear stress, which is 2.2 newtons per square meter. Then what happens? We are talking about the change in velocity, du. This change in velocity is the difference in velocity between the two plates, the one on top and the one below. The one on top is moving at 1.2. The one below is fixed, which means it's 0. So the difference between them is 1.2 meters per second. Difference in speed between them is 1.2 meters per second. Then we go back to our formula. So according to Newton's law of viscosity, this is what we have: shear stress, then we have mu du dy. We're looking for this viscosity here. So we make it the subject, and hence we have shear stress dy du. All we can do now is substitute the values because we have shear stress, we have the thickness, and we have this difference in velocity. So shear stress was 2.2 newtons per square meter. Thickness was 5 times 10 to the power negative 5. The speed difference is 1.2 meters per second. Then our mu therefore is 9.167 times 10 power negative 5 Newton seconds per square meter. This is normally expressed in poise. Poise, you just multiply that standard value, that SI unit, times 10. Then our final answer then becomes 9.167 times 10 raised to power negative 4. Example number 2. So here is a plate. We've been given the area, 0.6 square meters. And then it is supposed to slide at that incline, 30 degrees, velocity 0.36. Cushioning fluid is 1.8 millimeters thick, and this is the weight. Now, let's look at the data provided. This is the area, 0.6. The weight of the plate is 280 newtons. So here I have this, and this is the incline. I have some fluid there. Then what happens? I have this plate sitting here on top, supposed to slide down the incline. So that is the plate. Now, when you look at this one, the component of the weight coming down the plane is the one we're interested in. It's the one that will represent the force, because what we have is this, which is the weight of the plate, 280 newtons. By the way, we already have our angle here. So this is our 280 newtons. But then, before we get there, we're saying that the difference in speed, the plane is at 0, whereas the plate is sliding at 0.36 meters per second. The thickness of the incline, the thickness of this lubricant here, this one, between the plane and the plate, just this one here, this is 1.8 millimeters. So what do? You also convert it to meters. Divide this by 1,000. So your answer becomes 1.8 by 10 power negative 3. Then if you resolve, one thing you realize is that this one is our W sine theta, whereas the theta is the angle of incline. So W sine theta. W sine theta. So that's how come we have 280 sine 30. That gives us the force we're talking about, the shear force we're interested in, which is 140 newtons. So with this in mind, it already reminds us of one problem. We don't have the shear stress. The shear stress is force per unit area. Do we have the force? Yes, it's here. Do we have the area? Yes, right here. The area of the plate we're told is 0.8 square meters. Very good. Then let's go back and find the shear stress. Our shear stress is the force per unit tangential area. So force 140, area 0.6. Then what do we have? If you get the 2, we get 233.333 newtons per square meter. That is our shear stress. With this, we're now ready to handle the question. We can now find our viscosity. So this is our formula for viscosity. We already have the shear stress, the thickness of the lubricant, the change in velocity. So we can just substitute. 233.333, that is our stress, shear stress. Then the thickness of the lubricant, 1.8 by 10 power negative 3. This is now in meters. Then velocity is 0.36. So when you get that, it becomes 1.1667 Newton seconds per square meter, representing, if I multiply this by 10, I take this value, multiply it by 10 as per tradition, then my answer in poise is supposed to be 11.667 poise. Here's our third example. Glass Diameter 3 millimeters, immersed in a liquid whose surface tension is 0.5 newtons per meter. This is the surface tension force. Angle, 130 degrees. Specific gravity of the liquid, 13.6, meaning this is our mercury. And then calculate the level of the liquid in the tube. So we're trying to calculate the capillary rise, H. Now, the secret to this is to make sure that our information sits in right. Surface tension force is 0.5 newtons per meter. Then the specific weight of the liquid will mean you multiply the specific gravity provided by 9,810. So then we have 133,416. Diameter of the capillary tube is 3 millimeters. So you divide 3 by 1,000, then you have 0.003 meters. Angle, the theta is 130 degrees. So it seems we have all the data we need to calculate the capillary rise. And we can just now substitute that formula. This H is 4 that cos theta over WD. So what we do, 4 times 0.5, that was our surface tension per unit length, cos 130 divided by 133,416 times the diameter of the capillary tube, which is 0.003. So H becomes negative 3.212 times 10 power negative 3. What does that even mean? It means instead of going up, this height is actually below the free surface. That is our height, negative 3.212 times 10 power negative 3. So it actually went down. So that is simply referring to what we were discussing on the issue of capillary rise. Here is another one, last one. We have a plate, area 1.5 by 10 power 6 square millimeters, running at 0.4 meters per second. Then the thickness of the lubricant, 0.15 millimeters. Then we need to find the power, knowing that the viscosity is 1 poise. Data, our area should be converted to square meters. How do you convert from square millimeters to square meters? It's by dividing by 1,000 squared or dividing by 1,000,000. So these cancel out. Then you have 1.5. The velocity, it's the plate being put on a surface, meaning while the plate is moving, the other surface is at 0. So the du is still 0.4. The thickness of the lubricant is 0.15. So if I divide that by 1,000, I introduce 3 zeros in front of the 1.5. So 0.00015. Coefficient of, the viscosity that we're talking about, coefficient of dynamic viscosity, when it's in poise, we divide by 10. Because if it's in Newton seconds per square meter, we want to convert backwards. What we were doing is multiply by 10. So here we do the opposite, which is divide by 10 so that we can get it to the SI unit, which will align with the other units there. So once again, our area, 1.5. The du, 0.4 meters per second. dy, the thickness of the lubricant, 0.00015, then mu, 0.15. So then we're looking for the shear stress. The shear stress, we substitute, we have mu 0.1, du 0.4, and that one 0.0015. So meaning our shear stress is 266.667 newtons per square meter. But this is not all. We know that shear stress is force over area. And force, we make force the subject of the formula. We have to do the cross multiplication. So then our force will be shear stress multiplied by the area. So the area was given as 1.5. So if I multiply that by 1.5, I get my 400. Then this is the force. What about the power? It's supposed to be force times velocity. Power, force times velocity. How? We know that power is work done over time taken. Then we also know that work is actually force times distance. So force times that distance, which can be d or s or d. Then I still have the t here. So this last part here is representing my velocity. Firstly, I may decide to use something like s. So this is force times the velocity. In this case, it's the initial velocity. So force times velocity, force times velocity. So what do I have? It's 160 watts. 160 watts. All right, so there you have your exercise with 6 questions with all the answers planted there. Feel free to attempt them. And where you need to clarify, reach out or post a comment in the comment section. I'll definitely get back.